Demand for products is typically inversely related to supply. That is, in most circumstances, as prices go up, fewer people buy the products and more people want to sell their products. Example 2.5.8. Suppose that a company is trying to maximize its revenue in the two following cases. Case 1, in the summer when they charge $10 per widget, they can sell $1,200. Case 2, in the winter when they charge $20 per widget, they can sell $700. Their research suggests that a $1 increase in either season decreases the demand by 100 widgets. Should they increase the price in the summer, the winter, or not at all? Let's consider the summer case. The current revenue would be $10 per widget, sell $1,200, so the revenue is $12,000. With the price increase, it'll be $11 per widget. However, you lose 100 sales, so it'll be 1,100 that are sold. The product of 11 and 1,100 is 12,100. That is more revenue. With the price increase, the revenue also increases. Thus, increasing prices at this point is a good idea. Now let's consider the winter case when they charge $20 per widget. So the current revenue would be $20 times 700, product of which is $1,400 in revenue. Now, with the price increase, you're charging $21 per widget, but then you lose a sale of 100 of them, so only 600 sale. 21 times 600 is $12,600. With the price increase, the revenue decreases. Thus, increasing prices is a bad idea here. As demonstrated by the previous example, there are times when a given increase in price makes sense and times when a price increase does not. To determine prices to maximize demand, it is sufficient to consider the relative rate of change of demand versus the relative rate of change in price. This concept is neatly captured by the elasticity of demand. Economists use elasticity of demand to answer the question, when does an increase in price lead to an increase in revenue? Formal definition of elasticity of demand. Let the price P and demand X for a product be related by a price-demand equation of the form X equals D of P. That is, D is a function of the price P. Then the price elasticity of demand at price P, denoted by E subscript D of P, is the negative of the relative rate of change of demand divided by the relative rate of change of price. Let's observe, it is the negative of. To derive the equation, we set the relative rate of change of demand in calculus notation to d dp of the natural log of d of p. That is the relative rate of change of demand. We divide that by d dp, that's the derivative with respect to p of the change of price, which is the ln of p. Let's set that equal to the derivative with respect to p of the natural log of d of p is d prime of p, that's the derivative with respect to p, divided by d of p, and in the denominator, the derivative with respect to p of the natural log of p is 1 over p. Remember the negative. That is now equal to, let's simplify algebraically, the negative of d prime of p, that's the derivative with respect to p, divided by d of p times the inverse of 1 over P, which would be P over 1. Thus, simplifying, E sub D of P, that's the elasticity of demand with respect to P, is equal to the negative of, in the numerator, P times D prime of P, that is the derivative with respect to P, all divided by D of P. Example 2.5.9. For the price demand function, x equals f of P, which is equal to 100 times e to the power of negative 0.25p, part A, find the elasticity of demand. The elasticity of demand is given by the formula E subscript D of P is equal to negative P, the derivative of P, divided by just the demand function. For this problem, the demand is illustrated with F instead of D. Let's go ahead and find that derivative. So F prime of P is equal to 100, and then the derivative of e to the negative 0.25p. The rule tells us we also need to multiply it by the derivative of the power, and the derivative of negative 0.25p is negative 0.25. Let's multiply the constant. So 100 times 0.25 is just 25. Remember the negative. E to the power of negative 0.25p. Let's put it all together in the elasticity of demand formula. Then it would be the negative of P. The derivative is negative 25 e to the power of negative 0.25 times P, all divided by the function, which is 100 e to the power of 0.25p. The two negatives in the numerator cancel, so we would have 25p e to the power of negative 0.25p divided by 100 times e to the power of negative 0.25p. The e functions cancel, the p in the numerator stays put, and 25 over 100 reduces to 1/4. Note, revenue R of x is equal to P times x. That's P for the price times x the quantity. That is equal to P times D of P. D of P is the demand with respect to price. So, the derivative of the revenue R prime of x is equal to the derivative with respect to P of P times D of P. Now let's use the product rule. The derivative of the first, which would be P, the derivative of P is 1, times the second function, D of P, plus the first function, P, times the derivative of the second function, D prime of P. Let's solve for the revenue R prime of x, that is the derivative of x, greater than 0. That gives us a positive slope, and that tells us that the function is increasing. Replacing the R prime of x with the product form, we would have D of P plus P times D prime of P is greater than 0. Let's subtract D of P to both sides. Then P times D prime of P is greater than negative D of P. We will divide by negative D of P on both sides. That would get us to P times D prime of P divided by the negative of D of P. Let's set that equal to, we'll move the negative to the outside of the expression, negative, and in the numerator, P times D prime of P, all divided by the denominator, D of P, is less than 1. Let's observe that negative P times a D prime of P divided by D of P is the elasticity of demand with respect to P, and that is less than 1. Thus, if the derivative of the revenue is greater than 0, then the instantaneous rate of change of revenue is positive which means that the revenue is going up or increasing. Tying that in with elasticity of demand, we say that the revenue is increasing if the elasticity of demand with respect to P is less than 1. Similarly, if the revenue's derivative, that is R prime of X, is less than 0, then the instantaneous rate of change of revenue is negative, which means the revenue is going down or decreasing. That is, the revenue is decreasing if the elasticity of demand with respect to P is greater than 1. Now let's consider if the revenue's derivative equals 0. Then the instantaneous rate of change of revenue is 0, which means the revenue is not changing. The revenue is not changing when the elasticity of demand with respect to P is equal to 1. Now let's summarize all of that in the elasticity of demand table. For the value of the elasticity of demand with respect to P, if it is between 0 and 1, we say that it is inelastic, and inelastic means a price increase will increase revenue. If the elasticity of demand is greater than 1, we say that the demand is elastic. A price increase will decrease revenue. And finally, let's consider the elasticity of demand with respect to P equal to 1. The term associated with that is unit, and the effect on the revenue is that it corresponds to maximum revenue. Continuing with example 2.5.9, for the price demand function, X equals f of P is equal to 100 times e to the power of negative 0.25 P. Part B, find the value of P price that will maximize the revenue. Let's recall from Part A that the elasticity of demand with respect to P we solved to be P over 4. We just learned that you have maximum revenue with respect to the elasticity of demand, so E sub D of P, when it is equal to 1. So let's take the value we solved, which was P over 4 for the elasticity of demand, and set it equal to 1. Solving for P, we'll get $4. The price of $4 will maximize the revenue. Example 2.5.10. For the price demand function, X equals f of P is equal to 200 minus 4P, and a price of P equals $46. A, find the elasticity of demand. So we begin with the elasticity of demand equation. E sub D of P is equal to minus P. Let's go ahead and use F this time. So F prime of P divided by F of P. Let's find the derivative for the function F. So we write F prime of P is equal to minus 4. Putting it together, you'll have minus P times minus 4 for F prime of P divided by the function 200 minus 4P. Let's simplify this a little bit. So we'll come up here and we'll say the elasticity of demand with respect to P is negative times negative in the numerator will give us a positive 4P, and in the denominator we can factor out a 4, which will then be 200 divided by 4 is 50 minus 4P divided by 4 is just P. Canceling the 4's, we get that the elasticity of demand is P divided by 50 minus P. Let's go to part B. Find the elasticity at the given price and state where the demand is elastic or inelastic. So let's copy from the part A what the elasticity of demand equation was, and we got E sub D of P is equal to P divided by 50 minus P. Let's compute this at the price of $46. So elasticity of demand at $46 is equal to 46 divided by 50 minus 46, which would be 46 divided by 4, and that number is 11.5. Let's observe that 11.5 is greater than 1, and if the elasticity of demand is greater than 1, so let's go ahead and write if the elasticity of demand is greater than 1, we say that this product is elastic. And elastic means that a slight price increase will result in a revenue decrease. Part C, find the value or values of X for which the total revenue is maximized. This is going to be a two-step procedure, so let's first begin with X equals 200 minus 4P, and we are going to solve for P. So I would have 4P is equal to 200 minus X. Divide by P on both sides, and I'll get P equals 200 divided by 4 is 50. The next divided by 4 is X over 4. We solved previously that the elasticity of demand with respect to P was P divided by 50 minus P. However, we want this in terms of X, so every place we have a P, we're going to replace it with its equivalent 50 minus X over 4. So now we're going to have the elasticity of demand with respect to P of X, putting in 50 minus X over 4 every place there is a P. So the numerator becomes 50 minus X over 4, and the denominator becomes 50 minus, and for the P, we'll do 50 minus X over 4. We've got some algebra to simplify, and in the numerator, we've got 50 minus X divided by 4, and the denominator, 50 minus 50, cancels the negative and negative, gives us a positive X over 4. Let's multiply the top and bottom both through by 4, and the result in terms of X will be 200 minus X divided by X. Let's recall that maximum revenue occurs when the elasticity of demand equals 1. So for the 200 minus X divided by X, we will set this equal to 1. And that will give us 200 minus X equals X. I multiplied through by X, then 200 equals, adding X to both sides, 2X, and solving for X, I get X equals 100. The question that is asked is find the value or values of X for which the total revenue is maximized, and the value, that is the number of items, is 100. The quantity is 100. Example 2.5.11. Suppose the demand curve for widgets is given by the equation D of P equals 400 minus 8P. A. What is the elasticity of demand for the given demand function? To compute the elasticity of demand, E sub D of P, we complete the formula negative of P times D prime of P divided by D of P. The derivative D prime of P of the given function is negative 8. So let's assemble the formula. It'll be negative P times negative 8 divided by the function 400 minus 8 times P. The numerator, the two negatives cancel, so you get 8P divided by 400 minus 8P. Factor out the 8 in the denominator. So if you factor out 400 divided by 8, that'll give you 50, minus 8p divided by 8 is just p. Canceling the 8's, we get that the elasticity of demand is equal to p divided by 50 minus p. Part B. What is the elasticity of demand when the price of widgets is $10? Let's take the elasticity of demand equation we previously obtained. So E sub d of p is equal to p divided by 50 minus p, and evaluate this equation or this function at $10. So putting in a 10, every place there's a p, we'll have 10 divided by 50 minus 10, which is 10 divided by 40, and the value reduces to 1/4. The elasticity of demand when the price of widgets is $10 is 1/4. Let's recall that if the elasticity of demand is between 0 and 1, we say that the demand is inelastic. An inelastic means an increase in price. A price increase will result in a revenue increase. Part C. If the price of widgets is $10 and increases by 16%, what is the percent change in demand? We solve for this by looking at the definition of the elasticity of demand. That is, E sub d of p, if you'll recall, is equal to the negative of the relative rate of change of demand divided by the relative rate of change of price. What we need to do here is to solve for the percentage change in demand. So we're going to solve for the percent change in demand, and that would give us the relative rate of change of demand is equal to, let's carry the negative through, the negative of the elasticity of demand with respect to price times, and I'm going to shorthand relative rate of change to RROC of price. So let's compute. The relative rate of change of demand is equal to the negative of, and we computed the elasticity of demand with respect to P to be 1/4, and the relative rate of change in price is going to be a positive 16%. Multiplying the negative, the 1/4, and the 16%, you get negative 4%. Thus we conclude, so when the price increases by 16%, the demand will decrease by 4%. Example 2.5.12, consider the price-demand equation given by P equals 100 minus 250x. A, find the correct form of the demand function d of P. The demand function x is a function of P. So we need to solve the function we have, which is P equals 100 minus 250x, and solve it for x. That's right, solve for the variable x. I'll add 250x to both sides. So I got 250x plus p equals 100. Let's subtract p from both sides. So 250x equals 100 minus p. And to get x by itself, divide by 250 on both sides. Then we get x is equal to 100 divided by 250 minus p divided by 250. We can simplify this a little bit and get that x, which is a function of p, is equal to 2/5. 100 over 250 reduces to 2/5, minus P divided by 250. Part B. Solve for the elasticity of demand with respect to P and simplify. The elasticity of demand with respect to P is the formula negative of P times d prime of P, that's the derivative of d with respect to P, divided by d of P. In Part A, we solve for the demand with respect to price, and that function was 100 minus P divided by 250, and we simplified that to 2/5 minus P divided by 250. To find the elasticity of demand, let's go ahead and find the derivative of the demand function, and the derivative of the demand function is negative 1 over 250. Now let's put the parts into the elasticity of demand equation. So we would get that the elasticity of demand with respect to P is negative P. The derivative we obtained was negative 1 divided by 250. And the d of P function, we can either use the 100 minus P divided by 250 or the simplified 2/5 minus P over 250. I think the unsimplified version is easier to work with, so I will use 100 minus P divided by 250. Let's invert and multiply to simplify. So the numerator, the negative and negative, gives us a positive P times 1 over 250, and then for the denominator we invert and multiply, so we would have 250 divided by 100 minus P. The 250s cancel, and we finally get the elasticity of demand equation. For this function, it becomes P divided by 100 minus P. Part C. Determine the values of P, that's the price, such that the demand is elastic. Elastic means the elasticity of demand formula, we want it greater than 1. We solve it as P over 100 minus P, and we want that greater than 1. So let's cross multiply through the 100 minus P. You get P is greater than 1 times 100 minus P is just 100 minus P. Let's add P to both sides, and we get 2P is greater than 100. And solving for P, the price, we get P is greater than 50. So we have that the demand is elastic for prices above $50.